Okay, now finally we will address linear models regarding ANOVAs and regressions. So now we will have a change of scope because these techniques are more complex regarding a Bayesian influence. Okay, so these will they are grouped into having 3 or more variables, but also you can assume the one-way ANOVA scenario with only 2 variables, but it is okay if we have more than 2 groups. Okay, I will start with Bayesian one-way ANOVA. So now the test is not about specific means being equal or greater than each other. Now is that we have a model, and the model predicts the overall mean as H0, and also that model predicts a means of each group. As you can remember, the interplay in ANOVAs is between the within group differences and also or the overall differences versus the between group differences, and how we can predict better the data within this model. Okay, so now the model that we will create, and we create obviously more than one model, will have a probability of being true or a probability of being valid. Okay, so the Bayesian inference is going to be applied to that in the first place. So we will create a prior distribution for this probability to then create a posterior distribution for this probability. Okay, so if we choose non-informative priors, we can have a uniform distribution as an option, but also this distribution that is called R coefficient with scale 0.5. If we choose an informative distribution, we can choose a beta binomial distribution, a Wilson distribution, and other alternatives like Castillo, Bernoulli, or even a custom distribution that we can specify by hand. Whatever we want to choose, we will create a MCMC estimations with 10,000 iterations. That remember that we need to check that everything is okay to then try to describe the model. The results that we will have are bias factors towards the probability of including this model. That is, the probability of the model is going to be the prior, and the probability of the model given data is going to be the posterior. Okay. The posterior is also going to be given for the R dependent variable and an R squared. This R squared is also going to have posterior distribution with a credible interval. And also, we will describe the specific means with their credible intervals and their posterior distributions for each one of them. Okay. And finally, we can do some post-hoc comparisons that we will have some differences regarding the overall model with their own posteriors, credible intervals, and R squared. And finally, for assumption checks, we can have some cuckoo plots. Okay, so here's an example of an independent measures one-way ANOVA with non-informative priors. So as you can see here, we have a variable that is called treatment. Treatment has the levels control, drug A, and drug B, and the null model. So probabilities of the model are the same because our prior was non-informative. Okay, so now the probabilities of the model given data, the posterior probabilities, are basically 1 for the treatment and basically 0 for the null model. This is converted into bias factors. As you can see here, we have a very high bias factor on this and a very low bias factor for the null model, and can be converted into bias factor 1, 0. That is basically the maximum is set to 1 and the other ones is going to be set as lower. Okay, so you can have an analysis of effects here that have the same information but kind of different, because the probability of including this variable in the model prior and excluding the variable from the model prior, it's 0.50. That are exactly these ones. After that, the posterior probabilities of including and excluding the variable in the model given data are basically the same, as you can see here, 1 and very low. And we also have the bias factor of including this variable, that is this one, 500. Okay, so now from a plot, we can see and check the R squared of the model. So we have an R squared of 0.21 with a credible interval that is drawn from a posterior distribution. Here is the posterior distribution of the R squared of the model. That is the model that only takes into account one variable. Okay, so here we have this variable, this R squared, that the posterior distribution is very narrow and says that more or less the R squared is 0.21 with a credible interval of 0.21 and 0.22. Okay, now imagine that this is enough for us because we have very strong support that we need this variable to understand the dependent variable, so it's a useful predictor, and we want to describe it. Okay, so now here we have a table of all of the levels of our variable regarding also the intercept with the respective means, standard deviations, and credible intervals. This can be plotted because they are drawn from a posterior distribution. These posterior distributions are these ones. So you can see here that control is the red one, drag A is the green one, and drag B is the blue one. And you can also plot them point estimates with the credible intervals here. Okay, and also you can have some breakout plots for as descriptive information here. So now we can see that there are differences by group, more concretely regarding control. Control compared with drag A and drag B because it's higher in this variable. Okay. Finally, we have the QQ plot, as you can see here. It is interpreted exactly the same as the other QQ plots. The dots need to follow the red line. However, as you can see here, we have intervals, tiny credible intervals of each point. So if we have enough points with non-overlapping credible intervals regarding the red line, then it's evidence from problems of normality. Okay, so the next step should be getting a postdoc assessment of our variable, and as you can see here, we have control against drag A, control against drag B, and drag A against drag B. The prior odds are all of these. Then the posterior odds are going to be this, and as you can see here, control against drag A is very high, control against drag B is not that high but present, and drag A and drag B compared between each other has a very low odds. Converted to bias factor is this, as you can see here, so 800 as bias factor, 18 as bias factor, and 0.50. So now you can see here that we have an R squared for our model that is 0.22. However, the credible interval taking into account the postdocs is different, is larger. So as you can see here, it is different from 0. This is a very good news. However, it is around 0.2, but from 0.07 to 0.37, okay? And this is the descriptive information that we had earlier. So this is basically one-way ANOVA with independent measures. Using repeated measures, we have the same outlook. Non-informative priors, so the priors are basically the same probability of including the repeated measures or not. Then the posteriors, we have a strong support for including that. We have a high, very high R squared, around 0.8. And we have this really high bias factor regarding including this variable in the model. Now we have the means and credible intervals of all the three levels of our factor, that is day 1, 2, and 5. And as you can see here, day 1 and day 5 are negative, but day 2 is very, very positive. So the posterior distributions all say that they are very narrow. So as you can see here, there is basically a super overlap between day 1 and day 5, but day 2 is way, way higher. You can see that in this plot that is more simplistic and in the descriptive information here. So as you can see here, it is necessary to take into account this repeated measures factor to understand the dependent variable. And here the QQ plots, as you can see here, they have a different set on the independent group test because the credible intervals are way larger than the other one. But as you can see here, the tendency is basically the same as the red line. Now, regarding the postdocs, we also have prior odds for all of the comparisons. Posterior odds, as you can see here, day 1 versus day 2 is super high, and day 2 versus day 5 is also super high. Converted to bias factors is 51,000 and 48,000. And this is the same information we saw earlier, and we have a single model squared of 0.88. And even then, here we have a very narrow credible interval regarding R squared. So this is a pretty strong model regarding understanding the variable. Okay, so these are one-way ANOVAs. What happens if we have more than one independent variable? So it's going to be pretty similar, however, a little more complex, because we will have interactions and more than one model, okay? So the priors are basically the same, the results are going to be the same, but more complex. Here are one example. As you can see here, we do not have anymore only one model against the null model. We have a model of including all the saturated model, that is one variable, the other variable, and the integration, and the interaction. We also have, without the interaction, only main effects and only one of the variables each time. So we have a total of 1, 2, 3, and 4 models against the null model. We have 0.20 as the priors because it's non-informative. Then after taking into account the data, you can see here that the highest probability of all is the saturated model. Converted to Bayes factors is 1000 as the Bayes factor. The other ones is basically 0. And here converted into Bayes factor 1, 0. Okay, so this same information is in here, okay? And therefore, we need to include the variables. We need to include this variable and the interaction between them, because the posterior probability of including given data is basically 1 in all of them, and excluding the data is basically 0. So we need the three things, the three effects, 2 main and 1 interaction effect, to have a complete model. As you can see here, we have a very narrow R-squared posterior distribution around 0.7. And here are all of the means and credibility intervals of all of the factors, the main differences in each group, and also the interactions of them. And if we want it to be more visual, you can see here in the most simple of the plots that there is an interaction happening, because we have no differences between groups in 2 times, but in the time 70, then there is a group difference, okay? Reverse and traditional, the reverse is way, way lower, okay? This is present in the posterior distributions, if you like it. And for example, 70 and traditional, that is the pink one, okay? It's against one of the blue, that is 70 and reverse, that is over here. So there's a great distance, okay? We have the rain cloud plots with linked dots. I think it's pretty illustrative and pretty visual. And we also can create the posterior distributions for only the main effects. As you can see here, we have a main effect for the repeated measures and for the group, but the interaction is present. So we need to focus on the interaction, that it's here more crystal clear. Okay. The QQ plot, as you can see here, is basically the same as the repeated measures factor, so there are no problems with normality. Here we have the postdocs, but we only have the postdoc available for main effects. We don't have available posterior postdoc comparisons for the interaction effects. However, we can have this posterior R-squared distribution that is basically the same point estimate, but with larger credible interval. So yeah, this is basically a Bayesian two-way ANOVA. So remember that now the focus of the inference, first of all, is the probability of a model being right, and we just start to compare many models between each other. And when we decide to have our champion model, just describe it, their effects and its properties. Okay, now regarding Bayesian regression, we will also implement a linear model that is basically the same philosophy as Bayesian ANOVAs. However, our effects are not going to be expressed as means, but as slopes, okay, as a linear relationship between variables, okay? So, we will need basically the same set of priors as non-informative or informative, but now we need to create a criteria, and we need to specify which criteria we will need to use. For example, the Akaike information criteria, the Bayesian information criteria, or some alternatives like EB global, G prior, hyper-G, or JZS. It will create a MCMC estimation, but you can include Bayesian adaptive sampling as an alternative to MCMC if you want it, okay? So they will create some posteriors regarding if we need to include certain variable or effect in the model. We will have some bias factors regarding each effect, the prior and posterior probabilities of each predictor, as you can see here, probability of include as a prior and exclude as a prior, and include given data and exclude given data. We will also have some R-squared, the estimated slopes and their credible intervals, and also some QQ plots and residuals versus predicted plots for assumption checks. Okay, so this is an example of a simple regression with non-informative prior. We have the null model and one single predictor. We have 0.50 as priors and given data 0.95 regarding this variable and 0.05 of the null model, with 20 as bias factor. That's pretty strong, not super strong, but pretty strong. And we have the same information here, including and excluding prior and including and excluding posterior, the bias factor of inclusion that is converted as here, 20.73, but also here we have the descriptive information, means, standard deviations, and credible intervals of all of the effects. Okay, now we can plot them, and as you can see here, we have the mean, the posterior distributions of all of the effects. This is the posterior distribution of the potential intercepts with its credible interval, and also the posterior distribution of the slope in non-standardized scores with its credible interval. And you can also plot them as here with a point estimate with a credible interval. You can also have a QQ plot to check for normality, and also the residuals versus fitted plot. That remember that all of these scatter plot needs to be independent. So a dashed line here near 0 is available, but JASP will estimate here a non-linear try to see if there's a non-linear pattern going on. Okay, so here's an example with multiple Bayesian regression. And as you can see here, we have 4 variables, no, excuse me, 1, 2, 3, 4, and 5 variables. We have 5 variables in the model. And now all of the combinations between them, like only one of them, only 2, only 3, the 5 of them, etc., will be included in the model. Now the priors will be specified as them, because each variable will have its own prior, and because it's not informative, it will have the same. But if you amount one variable in the other, the prior will be affected. So this is a typical thing to happen. And now we have the posterior probabilities of the model being true given the data. As you can see here, the highest of them is this one, that is only including this variable, and also this one that is including these 2 variables. Converted into bias factors, as you can see here, we have 5 and 5, which is kind of weak. And we have an R-squared of 0.78 in both cases. So it seems that these 2 pairs of variables are basically the best models that we can have. The rest of the variables can be excluded because they are not informative. Okay. So this information can be plotted here, or plotted, no, displayed here in tables. These are the bias factor of the inclusions with their mean and standard deviation and credible intervals here. And now, regarding plotting, we have here all of the posterior distributions with their maximum point and their credible interval, and also a vertical line regarding 0 to see how far from 0 they are. As you can see here, left flexibility is overlapping with 0. It also happens with left strength and right strength. And yeah, kind of. And also right flexibility. The only one that is definitely not overlapping with 0 is bilateral strength. Okay, so you can plot that here in a more simplistic way. And as you can see here, bilateral strength is the other one not overlapping with 0. So it seems that there is the strongest variable is bilateral strength. And this plot is very informative. You can see the marginal inclusion probability of each of the variables with a dashed line regarding prior inclusion probabilities. So the good thing to happen is that the probability of inclusion overcomes the prior, okay? Or at least it meets the prior if you are working with informative priors, okay? So this plot says clearly that bilateral strength is overcoming the prior. However, right flexibility is overcoming just by a little bit the prior, okay? So, and the right strength does not overcome the prior. And left strength, neither. It's not overcoming the prior, okay? Finally, we have a QQ plot that will doesn't give any red signal about normality. We have the residual versus fitted plots also in a good way because they seem to be independent. And we have the model probabilities in a QQ plot that also are following the line, so there's no problem at all. So finally, if we need to choose a model regarding this Bayesian multiple regression, we could go for example, left strength and bilateral strength with a 78 R squared, or right strength and bilateral strength. However, regarding only bilateral strength, we have an R squared of 0.64. And as you can see here, right strength and left strength, that are these two variables, overlap with 0. So we don't have much evidence to affirm that they are actually doing something in the model. However, we have a complex output that says, in principle, the best model is bilateral strength that is clear that it has some effect. That is mostly around 0.3, I think. No, bilateral strength has 1.16 as an effect unstandardized format. Okay, so bilateral strength needs to be included. That's without doubt. However, what we do with left strength or right strength, because the R squared is elevated towards 0.78, and that's a good thing, but we don't have much evidence, or we don't have enough strength to affirm that their specific role is enough by themselves, okay? So this is one of the wonders of Bayesian regression, that they can be very complex, and they will lead you to interesting questions to make, and also to maybe create a more parsimonious model, only considering bilateral strength, and test if including or excluding left strength and right strength is okay, because remember, multiple comparisons are robust in Bayesian inference, so you can do that, okay? Okay, so this concludes the 4th session, and as you can see here, it's complex regarding ANOVAs and regression. So I think that I wish that many of you have learned a lot regarding how to use these techniques in JASP, and I encourage you to use them in your practice and in your research projects. Okay, so the final session will be about Bayesian psychometrics and more multivariate techniques regarding a Bayesian way. Thank you very much for being here. Bye-bye.